So, good morning, good afternoon, good evening, whatever time of day you guys are watching this. This will be the first of 4 lectures that we will look at while I'm in San Francisco. And what we'll be moving through the next couple of lectures, and I'm going to try to keep these at 25 to 30 minutes each, is allyl chemistry and then diene chemistry, and hopefully we'll be able to round those off in the space of those 2, 3, 4 lectures. So let's start with allyl chemistry. Okay, so let's start with allyl chemistry. You'll remember back from your 301 that if I look at an alkene, like for example propene, I can define the carbons of the double bond as vinyl, or some people say vanillic carbons. Okay. And obviously the protons attached to a vinyl carbon will be vanillic or vinyl protons. The carbon attached to the vanillic carbon is called an allyl, or some people say allylic carbon. Okay? And obviously the H's attached to the carbon, the allylic carbon, are called allylic H's, or allyl H's. Okay, so these are vanillic carbons, these are vinyl H's, right? Vinyl H's, vinyl carbons, this is an allylic carbon and an allylic H. It turns out that allyl species are very stable because regardless of the character of an intermediate at the allyl position, whether we're talking about an allyl cation, an allyl radical, an allyl anion, or some species that simply has a lone pair of electrons in that position. For example, I could have an oxygen here with a lone pair, and that won't be attached to, say, an alkyl group of some sort. I will have resonance. I would be able to stabilize the entity by resonance. Okay, so I'll be able to draw that resonance form, the positive charge here. So the hybrid then really looks like this. And there's a positive charge that is delocalized over the two. If I have an allyl radical, I can do much the same thing. It's a single electron transfer, however, and I'll have a species that looks like this. And so the hybrid then simply looks like that, with a dot. And you might expect, of course, that for the anion, my scenario will be very much the same, and I'll end up with this entity, whose hybrid I can draw like this. So regardless of the character of the intermediate at the allyl position, it is going to be resonance stabilized. But what I want you to notice is that these 3 species look very much alike. The only difference is whether they bear a charge or not, and if they bear a charge, is a charge plus or minus. And what this really tells us is that there really is a pi system that envelops not just these 2 carbons of the vinyl group, but it also envelop the allyl position. Now, by the way, remember I said that regardless of what charge, if any, the species carries, allyl entities are stable. So chemistry at the allyl position is relatively facile, because whether we're doing free radical chemistry, so we generate free radicals, or we're doing chemistry involving cations or anions, whatever I generate at the allyl position is going to be pretty stable. And I'm going to erase this one. This is not really an allyl entity per se, but you still get the point that the O is part of a system much like an allyl system, because I can use those electrons and delocalize those. And we saw those, for example, with enols and so on. Well, how can I describe the orbital picture of these allyl intermediates, right? How can I describe the orbital picture of these 3 allyl intermediates? Well, what it really means is I have 3 interacting p orbitals. Okay, I've got 3 interacting p orbitals. And I can imagine saying, well, you know, these 2 are probably here, right? Those are the ones in the pi bond. And then this position corresponds to this carbon. Okay? Nonetheless, I have 3 interacting p orbitals. You remember back from your Gen Chem and from your 301, because we talked about this at length in 301, that there's a concept of orbital conservation, that the number of orbitals I put into a system is the number I get out. So if I have 3 interacting p orbitals that are able to overlap in a side-on fashion, right? Able to overlap in a side-on fashion, well then I'm going to get 3 pi orbitals out of it. So 3 orbitals, 1, 2, 3, will give me 3 orbitals, which I will describe as 1, 2, 3. Because the overlap is sideways, I can designate these orbitals as pi. I'm going to call this one pi 1, I'll call this one pi 2, and I'll call this one pi 3. And I have ascending energy in this direction. What do they look like? Well, I can say that pi 1 will be formed by in-phase overlap of my orbitals. So I'll have plus, 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 minus, minus, minus. So in much the same way as I form a pi bond, where I have 2 p orbitals overlapping, so 1, 2 would give pi star. Alright? And what would they look like? Well, pi would be formed by in-phase overlap. Oh, good grief. Pi would be formed by in-phase overlap, and which is plus for plus, minus for minus. And pi star will be formed by outer phase overlap. Plus, minus, minus, plus. So that's what I've done here, right? So instead of having 2 interacting orbitals giving rise to 2 pi types, the side-on overlap, I now have 3 interacting p orbitals. Upping sideways, I'm going to get 3 pi's. Pi 1, pi 2, pi 3. The pi 1 would be formed by the orbitals overlapping in phase. What does pi 2 look like? Well, pi 2 looks like this, and it's the only orbital you will meet of the set that has what's called a null space, which is here. I'm going to have a plus, minus, minus, plus. And this null space is, and you have to remember, now, orbitals are calculations. They're probability functions as to where the electron will be found. And the probability is, well, in fact, when you do the calculations, there is 0 probability of finding an electron here. So it's a null space. There is no orbital in that position. What does pi 3 look like? And the answer is, well, pi 3, which does not have a null space, pi 2 is the only one that does, will have plus, minus, plus, minus, plus, minus. Right? It's formed by completely outer phase interactions. I know that not only is there orbital conservation, so the number I put in, 1, 1, is 2, is the number I get out, 1, 2. So here the number I put in, 1, 2, 3, is the number I get out, 1, 2, 3. But I also know that the number of bonding orbitals is equal to the number of anti-bonding orbitals. So if I look at my scenario with my 3 p orbitals, pi 1 must be bonding, pi 3 must be pi 3 star, which means it's anti-bonding, right? Pi 3 star is anti-bonding. The question is, what is pi 2? Pi 2 is neither bonding nor anti-bonding. Pi 2 is non-bonding. This is a new type of orbital. And a non-bonding orbital is one that doesn't contribute to bonding, but doesn't detract from it either. Right? It neither helps nor hinders. Well, one of the questions we're going to ask about these orbitals is, do they have any nodes? And what is a node? A node is a surface about which there's a phase change. So, for example, if I look at a p orbital, right, plus, minus, there is a node here. about which my phase changes from plus to minus. If I look at an s orbital has no nodes, right? There's no phase change in an s. I look at an sp3 hybrid, right? If I look at an sp3 hybrid, well, then it also has a node, right? There's a node here about which the phase changes. And in fact, in general, in any orbital that has p character, I'm going to have a node. I'm going to have at least one node. So how many nodes, if any, do I have in pi 1? And the answer is 1. There is the obligatory node in the plane of the molecule, which all p systems must contain. If you look at it, has a node in the plane of the molecule, right? That cuts right across the p orbit. And every orbital that has p character is going to have at least one node. This is what's called the obligatory node, okay? The mandatory node. So pi 1 has one node. Pi 2 has two nodes. There is the node that is obligatory in the molecular plane. And then there is another node here, about which plus goes to minus, and minus goes to plus. In pi 1, pi 2, and guess what?
3 nodes in pi 3. Node in the molecular plane, a node about which plus goes to minus and minus goes to plus, a node here, about which minus goes to minus. So first, okay, and what we're going to look at is, here again are my 3 pi orbitals. I'm going to designate them as pi 1, pi 2, and pi 3 star. And I'm going to be cheeky. Instead of writing the p orbitals, I'm just going to put plus, 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 minus, minus, minus. And this is a perfectly acceptable way of representing my molecular orbitals. I'll have a plus and a minus, a plus and a minus, and again there's a null space in the middle so nothing goes here. And I'll have plus, minus, plus, minus, plus, minus. If I were to ask for the number of nodes, there'll be 3 in pi 3 star, 2 in pi 2, 1 in pi 1. If I were to ask, if I would remember again, we're describing propene. I'm sorry, the propyl. We're describing the allyl intermediates. If I were to ask, well, how many electrons do I have in each of my 3 species? The allyl radical, the allyl anion, and the allyl cation. Well, certainly the allyl cation has 2 electrons in the pi bond, and I'm going to be really bad here, and this will be really bad. I'm going to put a dot and a dot for those electrons, and this p orbital is vacant. That's why it's a positive charge. So in all, I've got 3 electrons. So if I were to put my energy levels, that's pi 1, pi 2, and pi 3, then for the allyl cation, my system only has 2 electrons in the pi system. So according to the off-board principle, the first goes in pi 1, that's the lowest energy orbital. According to the Pauli exclusion principle, the second goes in pi 1 as well, as long as they're spin paired. So that the EC, the electronic configuration for the allyl cation can be simply represented as pi 1, 2. Right? The EC of the allyl cation can be represented as pi 1, 2. Well, what about the allyl radical? Well, the allyl radical, like all of my allyl species, will have 2 electrons in the pi bond, and then there's a dot here, which means there's 1 electron. So I've got 3 electrons in all. Well, where do they go? According to off-board, the first goes into the pi 1. According to Pauli, the second goes into the pi 1 as long as it's spin paired. The third electron, therefore, according to off-board, goes into pi 2. So the EC of the allyl radical is pi 1, 2, pi 2, 1. Obviously, for the allyl anion, where I have my pi bond and then a minus charge, which is tantamount to a lone pair of electrons, I now have 4 electrons. And so the fourth one occupies here, and the EC of the allyl anion becomes pi 1, 2, pi 2, 2. Okay. You'll remember that we had some discussion back in 301 about frontier orbitals. We talked about frontier orbitals. And the frontier orbitals are among the most important orbitals in chemistry because they dictate nucleophilic-electrophilic interaction. What does that mean? You remember we use the terms HOMO and LUMO to describe these orbitals. And what is a HOMO? HOMO is the acronym for highest occupied molecular orbital, and LUMO is the acronym for lowest unoccupied molecular orbital. And when a nucleophile donates an electron pair, it is donating the most energetic electron pair, and that is the electron pair found in the HOMO. So nucleophiles react via their HOMOs. When an electrophile accepts electron pairs, where will they put it? And the answer is in the lowest energy orbital that is vacant. In other words, in the LUMO. So nucleophile-electrophile chemistry, base acid chemistry, really happens because of HOMO-LUMO interactions. And it becomes critically important in many aspects of chemistry to know what your HOMO and LUMO orbitals are and what they look like. Because how they interact is dictated by what shapes they have. That's something we won't actually talk about in any kind of detail, just to mention that there's an importance to it. In fact, if you guys actually end up taking a graduate or an upper level undergraduate course, Chem 424 for example, frontier orbitals are an important part of that discussion. But for now, we just need to know what frontier orbitals are and to recognize that frontier orbitals are important. What we're going to do is we're going to designate our frontier orbitals for both the allyl cation, well, for all three, the allyl cation, the allyl radical, and the allyl anion. So let's go back. The EC of the allyl cation is pi 1, 2. So we've got 2 electrons here. So what is the HOMO of the allyl cation? What is the orbital of highest energy that has electrons in it? And the answer is pi 1. So for the allyl cation, HOMO is pi 1. What is the lowest energy orbital that is vacant? And the answer is pi 2. So the LUMO is pi 2. Right? For the allyl radical, I have 1 more electron. And therefore, if I would ask you, who's the HOMO of the allyl radical, the answer is pi 2. Pi 2 is the highest energy orbital that has electrons. Does not have to have an electron pair, it just has to have electrons in it. So the HOMO for the allyl radical is actually pi 2, and the LUMO is pi 3 star. For the allyl anion, where there's now an electron pair in pi 2, well then pi 2 remains the HOMO, and pi 3 star remains the LUMO. Okay? So I could ask you, well, that's all well and good, but what if I had, for example, this compound? What if I had 1,3-butadiene? And I asked you to draw the orbital picture for 1,3-butadiene and to draw all of my orbitals and to indicate which one, where my electrons are, what the electron distribution is, and to also indicate which ones were my HOMOs and which one was my LUMO. How would I do that? The first question I'm going to ask is, how many interacting p orbitals do I have? Because that dictates the number of orbitals I end up with. So really, in 1,3-butadiene, I've got a pi bond here, I've got a pi bond here, and since these can overlap sideways in this direction, they can also overlap sideways in that direction. And so what I have then would be 4 interacting p orbitals, right? And I'm going to go ahead and put an electron in each of these, which is a very silly thing to do because electrons aren't points.
but it certainly indicates that I've got 4 electrons in that species. Well, if I have 4 interacting p orbitals, I'm going to end up with 4 molecular orbitals, because the number I put in is the number I get out. So I'm going to grab some space here. Well, doesn't matter. So I'm going to end up with 1, 2, 3, 4. And I'm going to have energy in my ascending axis. I'm going to go ahead and put a plus here. Plus, plus, plus. And I'm going to designate my orbitals as pi 1, pi 2, pi 3, and pi 4. Now, I know that pi 4, which is the highest energy orbital here, has to be pi 4 star. I know that much. What I want us to do is to identify what are the phases in the other orbitals, where there are pluses, where there are minuses, and also to identify all of my anti-bonding orbitals. In other words, clearly pi 1 has to be bonding. In fact, if pi 1 is the lowest energy orbital, it has to be bonding, which means it must have been formed by in-phase overlap. So I can go ahead and say there's a plus, 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 minus, 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 minus. I can do that for pi 1. Heck, for pi 4 star, it's going to be completely scrambled. It'll alternate. So I'm going to have plus, minus, plus, minus, plus, minus, plus, minus. So I can always do the lowest energy orbital, the lowest energy molecular orbital, my LOMO, and I can always do my highest unoccupied, my HUMO. I can do those blind. The question is, what happens to pi 2 and pi 3? How are their phases distributed? And then secondly, I can have one of two scenarios. Either pi 1 is bonding, pi 4 star is anti-bonding, and pi 2 and pi 3 are both non-bonding. That's a possibility. The other option is pi 1 and pi 2 are bonding, and pi 3 and pi 4 star are anti-bonding. Which one is it? Well, the answer is really very, very simple. If I look at 1,3-butadiene, what do I have? I have 2 pi bonds. A bond cannot exist unless the bonding orbitals are occupied. So it must mean, since there are 4 pi electrons, 1, 2, 3, 4, which exist in 2 pi bonds, then pi 1 and pi 2 must be bonding orbitals, because I need 2 orbitals to hold my 4 bonding electrons. And I know I've got 4 bonding electrons because look, I have 2 pi bonds. So I can say pi 1 and pi 2 are bonding, which means pi 3 star and pi 4 star are anti-bonding, because the number of bondings must equal the number of anti-bondings. Okay, so I have indicated the character of my orbitals. What about the phases? So, I've got plus here. I need to indicate the number of nodes. So I'm going to write number of nodes, and I'm just going to clear some space here. And I need to calculate the number of nodes in my orbitals. Well, that's fair enough. Let's go nodes. How many nodes will pi 1 have? Absolutely right. It's going to have 1 node. That is the obligatory node in the molecular plane. How many nodes will pi 2 have? 2 nodes. Pi 3 star, 3 nodes. Pi 4 star, 4 nodes. And I can see the 1 node in pi 1. I can see the 4 nodes in pi 4 star. 1 here, 2, 3, 4. So for pi 2, I need to find a second node. I can do this in a couple of ways. Right, so I'm going to go to the side and work on pi 2. I can get 2 nodes, and of course there's 1 node in the molecular plane. So I can either say, well, I can have plus, 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 and then a minus here. Right, that's a possibility. So I'm going to have my node here. So that completes my 2 nodes. That's an option. Now, by the way, plus, 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 minus is equivalent to minus, 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 plus, right? Remember, these are just designations that distinguish the phases of my orbitals. It might as well have been boys and girls, or blue and green, or red and yellow, or shaded and unshaded. So these are equivalent. So this is one depiction of pi 2 that gives me 2 nodes. There is another option. And the other option is I can have plus, plus, minus, minus. And if I do that, this will be plus, plus, minus, minus. So I'll have my one node in the molecular plane followed by a second node here. Which of those is superior? And the answer is, it turns out this is the more stable version of pi 2. It is the one that we believe occurs in practice. And the reason is twofold. One simple reason is that it's symmetrical. And wherever possible, nature likes symmetry. And there is symmetry in this version of pi 2 that is not present in that version. But perhaps the more important reason, which I guess is linked to the symmetry, is that if if I look at pi 2, this version, every p orbital is involved in bonding. So this is in phase with that, so they bond. This is in phase with that, so they bond. Now, these two don't bond, so there's no through bonding, but I have this involved in a bond, that in a bond, this in a bond, that in a bond. All four involved in bonding. Bonding stabilizes. If I look at this version of pi 2, well, these three are in a bond, and it's nice because it's through bonding, but this one is out. And a scenario in which I have 3 atoms bonding and 1 not is not as stable, and therefore cannot contribute as much as the one in which all 4 are bonding. And therefore this is the version of pi 2. Well, if all 4 are bonding, why is pi 2 less stable, more energetic than pi 1, where all 4 are also bonding? And the answer is because in pi 1, not only are they bonding, there is through bonding. There is through bonding. And what this means is the atom on the far left can feel not only the atom next to it, but also this one and that one. Okay? Whereas in the case above, this atom feels and is felt by, is stabilized by this one. It has no interaction with those. So pi 1 and pi 2 are the most stable states of all, but pi 1 is the most stable state. What about pi 3 star? What does pi 3 star look like? I'm going to go work on this end. Let me just check my time to make sure I'm not going to run over here. What does pi 3 star look like? Well, I've got a couple options. Pi 3 star now needs 3 nodes. So I could have pi 3 star, well, of course there's a 1 node in the molecular plane, but I can do plus, minus, minus, plus, minus, plus, plus, minus, which will give me my node in the molecular plane. That's 2 nodes, and that's 3 nodes. That's an option. Or I could probably do plus, plus, minus, plus, minus, plus, minus, minus, which gives me my 1 node in the molecular plane, 2 nodes, 3 nodes. So I've got 2 possibilities for pi 3 star. Yeah, I don't think there's any other. Which of those is favorable, is more favorable? Well, there's no great amount of symmetry in one versus the other, although I would suspect that this structure is a bit more symmetrical than the other. But I would make my decision in the following way. And this is a bit of a stretch. I'm going to say, well, let's imagine that where the orbitals are in phase, they're going to form a bond. So at a stretch of the imagination, what this species represents, is kind of like an alkene that is mono substituted. because these are involved in a pi bond. What this one represents, on the other hand, is a scenario in which the double bond is internal, because these two are in phase. Well, which alkene is more stable? A terminal alkene that is monosubstituted, or an internal alkene that is disubstituted? The answer is, hands down, the di. Therefore, this version of pi 3 star is the one that is favorable because it represents a scenario where the bond is at its most stable. And so the version of pi 3 star, right, looks like this. All right, plus, minus. So that represents the orbital picture of my 1,3-butadiene system. So I can look at it in terms of the number of nodes. I can look at it in terms of bonding and anti-bonding and so on. There are no non-bondings in the P4 system. And one of the things I want you to realize, of course, is that the number of nodes is a measure of the stability of the species. So as the number of nodes rises, the energy content rises. And it's something you'd have realized already, because when we look at in a given basis set of orbitals, like say the S and the P's, the S is nodeless. The P has a node. You look at d orbitals, they have more than one node. So in general, as the number of nodes increases, the energy content increases. Well, what is the electron distribution, what is electronic configuration of 1,3-butadiene? Well, how many electrons do I have? The answer, I've got 4, because I've got 2 pi bonds. Aufbau says the first goes into pi 1. Pauli says the second is accommodated in pi 2 as long as they're spin paired. Aufbau says the third goes into pi 3, into pi 2, and Pauli says the fourth goes into pi 2. So the EC of 1,3-butadiene is simply pi 1, 2, pi 2, 2. Okay? Now, one of the points I want to make is that it does not matter what my system looks like. In other words, this molecular orbital diagram is true for 1,3-butadiene, as it is for this alpha, beta, and saturated ketone, as it is for this species, as it is for anything of that nature. Because all I'm interested in is the p-p interaction. And in all of these systems, there are 4 interacting p orbitals, so the system looks exactly the same as this one. Now there is a subtle difference, and that is because species like these, which have heteroatoms, also have lone pairs. And so I'm going to have to include the lone pairs in the pi system. Right? So I'm now going to have non-bonding orbitals, but in terms of the p system, in terms of the pi system, they look exactly alike. Okay, I'm sure I'm running out of time at this point. Yeah, I've got a minute left. So what I'd like you guys to do is to do the following exercise for me. I want you to construct the molecular orbital diagram, right, for, let's say, this species, which is the penta dienyl radical. And I want you to follow exactly the same exercise that I did, which is tell me how many interacting p orbitals there are, therefore how many molecular orbitals you get out, label them pi 1 through pi whatever, tell me which ones are bonding, which ones are anti-bonding, which ones are non-bonding, if any. And quite frankly, if I have an odd number, I'm going to have at least one that's non-bonding. I want you to indicate the phases on all the orbitals, and then I would like you to tell me what the electronic configuration of the species is. So I want you guys to try that one as an exercise, and we look at it when I come back on Wednesday. So this will end the first lecture on allyl chemistry. Thank you.